Hello, everybody. Welcome back to the MIT Category Seminar. Today we have Christian Williams from Riverside, who's going to talk about structural type for algebraic theories. Welcome, and please go.
Thank you. Thanks for the opportunity to speak. I've really been enjoying the seminar, and thank you all for being here. I'm excited to share this work. So yes, my name is Christian Williams. I'm a student of John Baez at UC Riverside. And today I'm going to tell you about structural types for algebraic theories. So first, I just want to explain what the title means. So this is not exactly standard terminology, but it's what I've chosen. Structural types are types that are built from term constructors and predicate logic. So for example, in the theory of monoids, you would have a structural type for an element to be prime, meaning that it is not the unit and it is not the product of two non-units. You can see that this is a predicate on the structure of elements of a monoid, essentially, because it's only referring to the term constructors of the theory and predicate logic. So our goal today is to present a method of generating structural type theories in order to provide languages with type systems that are intrinsic in the sense that they're not importing external notions of type and only the term constructors themselves. So just a few things I wanted to communicate first. The theoretical content of this work is relatively simple, and I want to say that it's more about the motivation and the future applications and connections. So this work is answering a question that I and a couple of collaborators have been wondering about for quite a while. It has a very concrete motivation that we're going to talk about. And that's why I find this work really interesting. So the work itself, even though it's simple, has a lot of interesting connections to topos theory and type theory and categorical logic. The main one being the notion of a logic over a type theory, which is one of the core concepts of categorical logic. And what this is doing is giving a slight extension of a form of logic over a type theory. And there's also connections to existing software programs such as Cave Framework. So I'd like to say that this is a fairly undeveloped introductory thesis, and it is to be implemented. So whenever you have ideas for connections or improvements or ideas about coding, please let me know. Although for the sake of efficiency, maybe we'll wait toward the end. But if you have any clarifying questions, please feel free to interrupt. And lastly, I want to emphasize that this work was completely motivated by Greg Meredith and Mike Stay. This would not exist if it were not for extended discussions with them over the past couple of years, and I'm very thankful for the guidance and motivation that they've been providing, and I'm excited to implement this idea with them. So here is the outline. First, I do want to explain the interesting and concrete motivation of this work, having to do with an existing software cooperative called RChain. And then we're going to lay out the basic framework. And overall, it's pretty simple. Basically, we're going to be modeling programming languages as certain kinds of algebraic theories. And we're going to embed the theory into the category of Presheaves. And then we're going to use the internal logic of the Presheave topos in order to construct these structural types. And then we'll give a brief application and a sketch of the type theory. And that last part is something that I would love input on to get a nice formal semantics of this. All right, so first of all, to start off with the motivation, RChain is a distributed computing system based on a concurrent language called the reflective higher order pi calculus, or rho calculus. So distributed computing system, there are similar endeavors nowadays that most people would refer to as a blockchain. But whereas most blockchains are focused on being a platform for transaction verification, RChain has the broader goal of being the foundation of a decentralized internet. And the main thing that sets RChain apart from existing endeavors is that it is based on a concurrent language rather than the vast majority of languages being sequential. So if you've ever heard of the pi calculus and you've wondered what it was about, the basic analogy that I like to think of is that the lambda calculus is to a computer as the pi calculus is to a network. And this is a slight simplification, but really I think it is about this simple. So the pi calculus is a concurrent language, meaning that a program is not a sequence of instructions, but rather a multi-set of parallel processes. And then computation, rather than being the successive evaluation of functions, is more about the interaction of parallel processes. And the reason why I think this is really insightful is that it provides a unified language for both computers and networks. Nowadays, we're seeing that those two notions are inseparable. So the basic rule is communication. So the way that you read this rule is that these are two processes in parallel. This bar is the parallel operator, and it's a commutative monoidal operator. And what these two processes are doing is that this one is outputting or sending, and this one is inputting or receiving. And these letters are names. The basic stuff of the pi calculus are names, and they function as both communication channels and data to be sent on those channels. So what this process is doing is that it's sending on the name n, treating it as a channel. And what is it sending? Some name a, which is treating it as like a data of some kind of pointer. This process is listening or inputting on the channel n. And then it has a process with a hole in it where it doesn't know what it's going to receive yet, but whatever it does receive, it's going to plug into that hole. And that's exactly what this communication rule says. This data that was being sent is passed through and plugged in to this process with the hole. So if this looks somewhat familiar, you can think about it as basically being like beta reduction of the lambda calculus, except now it is located at some name. And that name you can think of as like a location in a network. It could be a particular computer, or it could be a location in memory inside of one computer, or it could be something more larger and more abstract. So this is the basic idea of the pi calculus. And when you think about making a decentralized internet efficient, it might make sense or be intuitive that you would want a language in which parallelism is built in from the very beginning. So the language of RChain, the row calculus, takes that idea and adds one more layer of niceness called reflection. Reflection are these operators which turn processes into names and vice versa. So whereas in the pi calculus, you have to import a countably infinite set of names, which are basically just atomic symbols that you're going to use as locations or pointers. In the row calculus, you don't need to do this because anytime you need a name, you can take any process, any program, and you literally just put quotes around it. And now suddenly it's a name that you can use as a channel or as data. And then we also have an operator going back that can take any name and turn it back into running code. So now the communication rule looks almost the same, except now instead of just passing a little pointer, you can actually pass a whole program. So you can have some arbitrarily complex piece of code, and you can send it along a channel as easily as sending like a text message. So the rule here is that now you're outputting some process, Q, and when it gets passed, it uses this reference operator that turns it into a name, and then it's plugged in to this process with a whole. And other than that, the language is the same, but this idea that you can control the distinction between data and code adds this next level of self-reference to the language that is very powerful. So what does this have to do with this structural types business? So the idea is that names are being used as both the data and the communication channels in this language. And through this idea of reflection, one of the big benefits is that names, rather than being atomic symbols, they have as much form as processes, as programs. So if you're using these names as locations in a network, the fact that they now have form gives large-scale structure to the networks that you build on top of the row calculus. So the original motivation for this work is something called Namespace Logic, which aims to use this structure to think more globally about the web. So yes, so Namespace Logic is a framework for this reasoning, and Greg Meredith and Matthias Radestock, in addition to inventing the row calculus, a few years later wrote a paper called Namespace Logic for this purpose. And essentially what it is that it takes the language of the row calculus and just augments the signature with predicate logic and recursion. And then you use this language by constructing formulae. And these formulae are predicates on the structure of terms in the row calculus. And you use these as types in order to condition programs, like in the same way that you usually use types. So for example, in exact analogy with this prime example for monoids, you could have this predicate for single-threaded processes. So a process would be single-threaded if it is not the null process. There's this process that does nothing. And it's not the parallel of two non-null processes. So the reason why you might care about such a type is a lot of the complexity of concurrent computation comes from the fact of having many, many processes running in parallel. And you need to choose an actual ordering of events, be it a poset or a directed acyclic graph or whatever. This is a lot of the complexity that people think about in the context of blockchain consensus. So if you wanted to deal with this more systematically, you might want to take a huge parallel process and first break it down into the single-threaded processes. And then you build them back up and you're testing each time whether you get race conditions and that kind of thing. So this is a simple example of a type that namespace logic would want to consider. So our goal is the question, how do we construct this logic generally? How do you formalize this algorithm of blank plus predicate logic plus recursion? And so the basic idea is that we model the programming language as some algebraic theory, and then we embed it into Presheaves, and then we compose that with the subobject functor. And specifically, we're going to use the lax structure of the subobject functor in order to lift the operations of the theory to the level of predicates. And that will be how we get, for example, this parallel here is not really the original parallel because it's acting on the level of predicates rather than terms. So essentially, we're going to make sure that we get a model of the theory in the category of posets of predicates. All right, so this is just the introductory motivation. Please let me know if you have any questions. So now on to something that's probably more familiar to everyone, algebraic theories. So algebraic structures are presented by a set of sorts S operations F and equations between them. And I like to think that this is taking the usual idea of presenting a group by generators and relations, and it's raising it to a meta level where you are presenting the notion of a group by the generators being the multiplication, inverse, and unit, and the equations being the equations of a group. So for example, we have the theory of a monoid is something with a binary multiplication and a nullary unit so that it's associative and unital. And you take this presentation and you form the free Cartesian category on the presentation. And this is the algebraic theory of monoids. And what is special about it is that it represents the monoid functor. Cartesian functors to some category C are monoids in C. So so normally the definition of the two category of algebraic theories is really just the two category of Cartesian categories, categories with finite products. But we just want to make a slight adjustment because we want to reference the generating sorts for our purposes. So we refer back to the definition of an S-sorted algebraic theory where you have some fixed set of sorts S. And essentially what this definition is doing is that for each set, you get a category of, well, you get a two category of S-sorted algebraic theories. And what this definition is doing is just gluing all those together using some two categorical version of the growth and deconstruction. So, but all that it boils down to is the usual definition that a multi-sorted algebraic theory is a Cartesian category T, equipped with some identity on objects Cartesian functor. Identity on objects Cartesian functor. Identity on objects Cartesian functor. Could somebody mute? There was an echo. Thanks.
Yeah. Oh, I'm sorry.
That's okay. It boils down to the usual definition, except now we have the ability to reference the generating sorts. So when I say algebraic theory, you can just think of a Cartesian category. And then the category of models of some theory in some context C is the functor category between them. But if somebody knows a cleaner way of doing this, feel free to let me know afterward. All right, so while algebraic theories are very pervasive and useful in math and computer science, there is one construction that algebraic theories cannot express, which is really crucial to most programming languages, and that is the concept of variable binding. So if you have an expression with a free variable x, and you want to form the function that sends x to e of x, that is lambda abstraction. And anytime that we are forming functions or elements of HOMs, we're implicitly using some kind of lambda abstraction. So, you know, anytime that we're forming a program that takes an input and knows how to substitute in that input, we are using variable binding. So in order to apply this idea to programming languages, we need a notion of theory that allows for binding operations and a definition of capture avoiding substitution. So the earliest work that I know of that's explicitly categorical and informal is Abstract Syntax and Variable Binding by Fiore, Turi, and Plotkin. And they describe operads with operations which can bind variables. And the main insight is that exponentiating by representables is context extension. So their main running example is capital lambda is a functor from finite sets to sets that takes in some natural number n and gives you the set of lambda terms that you could form within free variables. So application would be a normal binary operation from lambda squared to lambda. But the thing that's special about lambda abstraction is that there's a change in context. Up here, you have a context with a distinguished free variable. So this would be like in the context of n+1. And then after the inference rule, you only have n variables. So in order to model this change in context, you use this idea of exponentiating by representable. And when you work this out, this is the definition of exponentiating in the Presheaves category. Then you use the universal property of coproduct and then the Ionnet lemma. And then you can model lambda abstraction as a natural transformation from this exponentiation back to lambda. So this was written quite a while ago. And more recently, it has been distilled from the operad perspective back to the more familiar algebraic theory perspective. And essentially what it boils down to is some Cartesian category with some exponentiable objects. That's really all that it is. So just to review that definition, an object S in some category T is exponentiable, Cartesian category T, if you have these objects T to the S, which represent terms of type T with a free variable of type S, equipped with a map evaluation which represents substitution, plugging in something of type S to get something of type T, which satisfies this universal property. And of course, what it means we need to preserve exponentiable objects, and we call F exponent if it preserves all exponentiable objects. So, so that leads to the definition of a second order algebraic theory. So what it amounts to is a Cartesian category equipped with some set of exponentiable objects. That's really all it is. And then we do this gluing thing so that we can, that we can have all possible generating sorts, but still reference the generating sorts. This is the result of a referee report that was concerned that things were dependent on a presentation when really I only needed the generating sorts. So that's why we're doing this. But yes, so it's just a Cartesian category with some exponentiable objects. And so at this point, you might wonder, why aren't we just using Cartesian closed categories? People have done that for a long time. You have higher order lambda calculus built into any Cartesian closed category, and then you could just write some theory inside of there. And that's true, you can do that. And a second order algebraic theory is a restriction of Cartesian closed categories. But the reason why it's still a useful concept is that it retains the classic monadicity results that we associate with algebraic theories. There is theory monad equivalence for second order algebraic theories. And recently, I think Dylan McDermott and Nathaniel Arcor characterized it nicely as certain strong monads. Second order algebraic theories correspond to certain strong monads on the category of Levier theories, actually, or algebraic theories more generally. So that's why we care about this, is to retain that connection to universal algebra. All right, so now that we have second order algebraic theories, we are in a position to give a theory of this row calculus that is the language of RChain. So it's pretty simple. It only has a few operations. You have one for parallel, a binary operation to put processes in parallel. You have the do nothing process that you build everything up from. You have reference and dereference that turn processes into names and vice versa. And then you have the two basic things that a process can do. You can either send on some name, some process, or you can receive on some name, and then you continue with a process with a free name in it. And the basic equations are the communication rule, like we were talking about. If you're sending and receiving on the same name in parallel, then this program, this process, is turned into a name using the reference operator and then passed into this process with a whole. And then we have this equation for evaluation which allows you to take any name and turn it back into running code. And finally, processes with parallel and the null process form a commutative modeling. So this is the theory of the row calculus, and you can see that it's a second order algebraic theory because we really need input to bind a name in order to define communication. So you can write this rule as a certain commutative diagram in the theory. The last thing I want to mention that we're not going to have time to get into is that you really don't want to consider these as equations. It's pretty unnatural to think about going backwards here. You could take any process with a name and pull the name out and do this reverse communication. And that would destroy the subtlety and non-determinism of concurrent languages. So we really want to think about these as directed. And so this is something that we were thinking about for quite a while because there seem to be quite a few ways to add behavior to a theory. There's enrichment, there is coalgebras. Both of those seem like good options, but they add quite a bit of complexity, especially when you're considering this framework of taking Presheaves and using the logic of the Presheave topos. So Mike Stay actually had this really elegant idea of simply adding in the theory of graphs into this theory. And then communication, rather than being an equation, would be an operation into a new sort E for edges. And then you say that the source of that edge is this redex, and then the target of the edge is this reduct. And it turns out that this idea meshes really well with this construction that we're going to talk about, and you can actually recover all of the operational semantics of this language. So we could talk more about that afterwards if people are interested in this question of dynamics in a theory. All right, so the other ingredient that we're going to use is the concept of a presheaf. So this is probably familiar to most people. Presheaf on a category T is some functor A from T off to set. And we can understand A as data on the objects of T. And of course, there's a natural way to embed T into the category of presheaves on it, called the Oneida embedding, that sends any object to its representable functor and any morphism to the post-composition morphism. And it's one of the nice things about the Oneida embedding is that it is Cartesian closed. So for example, if T is a second order algebraic theory, then this Y is a model of T in the category of presheaves. So the idea is that the Oneida embedding is nice and preserves everything, but then we're going to take subobjects, and that definitely does not preserve products and exponents, and we're going to have to use the lax structure to recover a model. So the category of presheaves is a topos with a category with rich internal logic. The finite limits are given pointwise. Exponentials are given by this formula that you get from the Oneida lemma. And the subobject classifier is a functor which sends any object S to the set of subfunctors of its representable. And this functor really contains all of the information that we care about in the construction that we're presenting. Because these subfunctors are really going to be our types. So we can interpret these subobjects as predicates, and then we have the logical constructors, the blank plus predicate logic that we're talking about. So for any presheaf A, the subfunctors of A form a hiding algebra. They're ordered by inclusion, which gives you a poset. Meet and join are defined by pointwise intersection and union, which gives you a lattice structure. And then implication is defined using this formula. So a lot of the time, Presheaves are really as simple as indexed sets, but every once in a while with a more subtle operation like implication, you need to be careful and make sure that things are still closed under precomposition. But this is the formula. The other nice thing about the subobject functor is that it is a hyperdoctrine, which means that for any natural transformation between Presheaves, we get a triple adjunction between their posets of subobjects. It's very nice, and it's in exact analogy with the situation for power sets. So any function between sets induces this triple adjunction where the middle adjoint is pre-image, the left adjoint is direct image, and the right adjoint is less, I guess, less talked about, less used, but I haven't even found a standard name for it. Maybe one of you knows. I'm calling it saturated image. Essentially what it does is normally if you just took some subset and you sent it to its image, and then you took its pre-image, it could get a lot bigger. But sometimes it might be useful to send your subset to the largest subset of the image so that its pre-image is completely contained in the original subset. So you could think about this as some kind of security property that you are getting only the things that could have come from your subset. So anyways, this example with sets is a sufficient intuition to get an idea for these formulas which generalize to Presheaf categories. So, so as the notation and the foreshadowing has been leading to, we are really concerned with the subobjects of the representables. And these turn out to be equivalent to something called sieves. So a sieve on some object S is a class of morphisms into S, which is closed under precomposition. So these sieves are equivalent to subfunctors of the representable on S. And I can give a better intuition why afterwards, but I want to make sure that we're good on time. So while the idea of a subfunctor of the representable might seem more abstract, when you think about some subtree, you have the tree of all morphisms going into an object, and we're picking out subtrees. These are the types of programs that we're going to be manipulating using this framework. So the simplest example of a sieve, besides the maximal sieve being the all morphisms into an object, any morphism in the category T generates a singleton sieve. So F going from R to S generates a sieve where you say, give me all morphisms that factor through F. So any operation in the theory is going to generate a singleton sieve. So from now on, we're going to use the subobject functor where we choose the left adjoint covariant action, the existential or direct image. And our goal is that we want to get a direct correspondence between the operations or the term constructors in the theory and the operations on predicates. Essentially, we want to make sure that we have a model of the theory in the category posets. So the subobject functor does not preserve products, but it does have a lax Cartesian structure. And we can use that to lift some operation A times B to C to, if you have a sieve on A and a sieve on B, then you take all possible pairs of them in order to get a sieve on A times B, and then you can pointwise evaluate this operation F. And the way that this lax structure is defined is that given a subobject of A and a subobject of B, you literally just take their product in order to get a subobject of the product. It's very simple, nothing fancy going on. And this is right adjoint to the canonical Colax structure. Every functor is Colax with respect to products. So in the terminology of Brendan Fong and others, this would be saying that the subobject functor is adjoint lax with respect to products. Maybe that was David Spivak as well, I'm not sure. So while it is pretty well known that the subobject functor is this adjoint lax with respect to products, it is also adjoint lax with respect to closed structure. This was an interesting thing to wonder about and find to be true. And this is going to be crucial for lifting operations which involve the exponentials. So the lax structure with respect to products induces a lax closed structure with respect to the exponentials, which is just given by currying of evaluation. So given some subset of functions, this induces a functor of power sets by essentially just currying evaluation and point-wise evaluating the functions. And the same thing is true for Presheaves. So the question is, essentially, how can we go backwards? So given some function or operation which involves an exponential, how could we lift this one to power sets or to the subobject posets? So so what it has to do with is the idea of a function respecting a functor. So if we imagine going backwards here, you have some functor from the power set of A. I'm just using sets for all the intuition. If you have a big F going from power set of A to power set of B, and you want to get a subset of functions from A to B, you think of big F as a rule which takes in some subset U and gives you F of U to be some subset of B. And this is a rule saying that, okay, all of U functions, if you take something in U, you have to land inside this F of U. And that's exactly what ends up forming the right adjoint to this lax closed structure. So here's the formula in terms of Presheaves, but essentially it's saying that a natural transformation respects a functor between the subobject posets if its image on every subfunctor is contained in the on where this big F sends that subfunctor. And this indeed gives a right adjoint to the lax closed structure. You're sending each big F to the set or the subobject of natural transformations from A to B that respect big F. So this is giving that it is that the subobject functor is adjoint lax with respect to closed structure. Sorry if I've been going fast. Please let me know if you have any questions. All right. So now putting these two together is going to give us a way to lift the operations of the theory to the level of subobject posets. So let T be a second order algebraic theory and consider some operation. So, so an operation would go from a product of exponentials to some object. And you can think of this as some n-ary operation, like in a normal algebraic theory, except you also have the ability to bind in sub I sorts in the ith coordinate. That's what this operation is doing. And so we can define a lifting with this long formula. We don't need to go through all the details, but essentially here, if all of these binding parts had been empty, then this is just some normal in-array operation. Then you can ignore this half, and all that this part is doing is that you have a product of sieves on some objects t sub I, and you turn that into a sieve on the product using the lax structure. You just, pointwise pair all of them, and then you're just taking you're evaluating the operation on all of those pairs. So for in-array operations, it's not doing anything too crazy. And what this part is adding is also dealing with the binding structure and making sure that we're only getting pairs that respect these rules. So up here, these are originally rules that are maps from sieves to sieves. So unpacking all of this, we get a formula that for this lifted operation, it takes in a bunch of rules, and if these are empty, then this collapses to the normal case of these just being sieves on t sub I, and it gives you the evaluation on all the terms which respect those f sub I. So this gives us a main theorem that we are getting, this lifting is giving us something like a model of the theory in posets. We're basically like forcing the composite of the Oneida embedding in the subobject functor to preserve products and exponents using this lax structure. And the only caveat is that it's going to turn out to be a Colax functor, and we're going to see why. But this is the theorem. And we probably don't have time to get into the full proof, but I'm just going to outline what the functor is doing. So on objects, it's sending a general object in a second order theory is some product of exponents. Exponential objects. And it's sending it to the product of exponents of the poset of sieves. And for an operation that's going into a single generating object, we're sending it to the lifting that we just defined. But a general operation in a theory goes from some product of exponents to another product of exponents, because those are the general objects. So the way that we lift those is a little bit more involved. We use the universal property of the product to say that this is just an n tuple of operations. And then for each of those in the n tuple, we uncurry this exponent part so that it's of this form. And then this is a form which we already know how to lift. And then we lift all of those, and then we just recurry and retuple them. And that's how we lift a general operation. So you can see this is why we needed to reference the generating objects, so that we know we can pick any object and know exactly how it is a product of exponential objects. So we'll talk in a minute why this is Colax. So this is my current attempt at packaging up the information, but I do think there will be a much nicer semantics. But the theorem is that the map which sends a second order algebraic theory to this model in posets defines a two functor from second order algebraic theories to essentially these quote Colax models in posets. But yes, to make this more concrete, we return to the example of the row calculus. So we abbreviate the image of any sort as S sub omega, and this means sieves on S. And then the data provided by this model, omega t, gives a lifting of the signature, so that you have this exact correspondence between the term constructors in the original row calculus and now these type constructors in this this augmented version that I'm calling the omega row calculus. And this exact correspondence actually gives that these constructors are automatically polymorphic, because there's an exact correspondence between the term constructors and type constructors. So other than that, it looks exactly the same. It looks like the same signature for this language, except now we're operating on the level of sieves rather than individual terms. So now, for example, we can construct this one for single-threaded processes because we finally have this lifted parallel, which is operating on sieves rather than terms. And of course, we got the logical operations from the hiding algebra structure of these posets. So, but a more impressive example, I think, is what happens when you think about lifting the binding operations, and you actually gain significant expressiveness. So in the same way that input binds a free name variable, and that's how you know how to substitute in a name later, in this lifted input as a type constructor, it's going to bind a quote unquote namespace variable. It's going to take in a rule from that takes in sieves on names and goes to sieves on processes. And this is very expressive because now you have a way to say, oh, this program, depending on which namespace that it is receiving data from, it acts these different ways. So in the untyped language, an input process, all it does is receive data on some name n, and then it plugs into some process. It has no idea what it's receiving, and it doesn't have any higher reasoning about how it's changing its behavior based on what it receives. But in this omega row calculus, a term of this type, when you use the lifted input, you take in some namespace and then some rule, some predicate context. Then terms of this type would be processes which input on some name in alpha, and then when they receive some name of type chi, they continue with some process of type phi of chi. So now this is kind of like a dependent function type, basically, that we're getting for free, that this process can change its behavior based on the type of name that it receives. And one example use of this that I think is really exciting is that you could use this typed input to design structural queries, which are programs that search not by external attributes, like when you Google by keywords, but you can search by the actual structure of code, because when you receive something of type chi, you can behave based on the structure of that name. So I'm really excited by that application. Now, some of you might have been a little nervous when I mentioned that the model that we're getting in posets is Colax. So there might be a way to fix this. I'm not sure. But from thinking about it so far, I think it might be inevitable when we consider this idea of lifting binding operations. So just to give an example what this Colaxness means. By Colaxness, I mean that it's not preserving composition perfectly and we're getting an inclusion. So consider this composite program in the row calculus. This is something that takes in a name and a process and then gives you the process which listens on that name, receives something, and then it outputs on that something some process. So this is a composite. So we can compare lifting the composite versus lifting separately and then composing. So if you, the idea is that if you lift the composite, then this X was already bound. As soon as you piece those together and you plug something into a binding operation, that X is bound, and then this, this lifting doesn't see that. And this type has to take in some name and then do nothing to it. It keeps it the same. But if you lifted them separately and then compose, this lifted input now has a chance to bind on the type level. So now you get the more general form where you can take in something of type beta, take in a name of type beta, and then output on beta. But it could be something different. So this allows for like some kind of endo transformation that keeps you inside of a namespace. So we get an inclusion from this one into this one, and that's why we're getting this colaxness. So yeah, the lifting of the composite doesn't see the type level binding for the constructors, while the composite of the liftings does. So to be honest, I'm not sure exactly how this affects the logic or the type theory that we get. But when you see this example, it's a pretty reasonable distinction. And it doesn't seem like the end of the world to me. I think you have both of them available and you have the colax structure relating them. So Baez always says, it doesn't make sense to be disappointed in math because it is what it is. So, so yeah. I think I'm short on time. But just to give one more example of an application that I think might start to communicate the expressiveness of this type theory, comes from an example used in namespace logic. So the last ingredient that we haven't built in yet is recursion, or fixed point operators. And we get these for free because when we take these posets of subobjects of representables, these are always complete and co-complete. So we can take whatever limits and co-limits we want. So given any natural transformation between these posets, we can take their limit and co-limit. Or specifically, if we had some endo functor on one of the posets, we could construct their least fixed point and greatest fixed point. These are really useful when we want to talk about formulas which are predicating over like the entire lifespan of some process. For example, you know, there's a way to make recursive processes that run forever, and you would want to make sure that they always satisfy a certain property. So that's the last example. And I really like this example. I think it's really cool. So two important properties of a distributed system are liveness and safety. So if you have some namespace, some set of you know, locations in a network of names that are trusted by some organization or some community, then liveness says that your system can always communicate on alpha. And safety says that your system can never communicate on not alpha. So, you know, it's secure that it's not going to share secrets outside of alpha. So we can express both of these properties in this single formula here. It's a recursive formula. And what it says is these are the type of processes which listen on alpha, and they don't listen on not alpha. And then the place where this recursion comes in is that it says, and also whatever you do next after this continuation also satisfies the same formula. So this is saying throughout this processes which throughout their whole life cycle can only listen on namespace alpha. So in effect, this is creating a compile time firewall. And I just think it's so cool that you can write this as such a short formula. So anyways, here is a sketch of the type theory that we get, but there's actually more. There's more than this. And one of the main next steps is to get a really nice formal semantics of the structural type theory. Because right now, you know, this is ignoring the hyperdoctrine structure. Once we mess with the lax stuff and we choose a certain image of the operation, we lose all of the nice adjoints that we had for the hyperdoctrine structure. So there should be a really nice story where we fit all of this information together into a category. So that is the next step. So that's it. Thank you very much for listening. You can find the paper on GitHub. And if you have ideas for connections, improvements, coding, or collaboration, feel free to contact me.
Thank you so much. Okay, are there any questions or any comments?
I'm happy to offer a couple of comments, but since I've been involved with the work, I want to give other people a chance first.
Yeah, so Greg can say a lot about all of this stuff. So in the if he has time in the discussion afterwards, feel free to ask him about this, about all of it in the future applications.
For now, there's some appreciation that people are showing on YouTube.
Oh, great.
So let me just make two very quick points, and then I'm sure there'll be room for other questions. But one is that this really nice property of bisimulation and its relationship to virtually all other forms of equivalence proposed in concurrency theory, as well as notions of logical equivalence. So what we want to do is to sketch out or identify the relationship between the logical equivalence that's implied here. So a term P is going to be logically equivalent to a term Q if and only if they satisfy exactly the same set of formulae that are provided by the type system. And what we'd like to do is to say, you know, under what conditions that is corresponds to bisimulation. So, for example, Hennessy-Milner logic, they coincide exactly. With spatial logic from Kairos and et al., you don't get that correspondence unless you add back in the observations associated with PAR. So what we'd like to do is to see under what conditions we get logical equivalence coinciding with bisimulation. And then the other point I just wanted to observe is that, you know, one of the key research goals is to be able to program at the collective level. So if you think about programming, genetic programming or molecular programming or biochemical programming, you need to be able to get ensembles of things that are all largely autonomous but yet have very similar code to, you know, adhere to, you know, or to work together to achieve some property or some result. And your theorem, Christian, is nice because it's a small step in that direction. So what you're saying is the predicate gadget that you get at the end is already a model, so you can program at that level. So you're programming ensembles terms rather than terms themselves.
Yeah.
So it's a step in that direction, which is very nice.
Yeah, thanks. Yeah, the whole question of how much more you can do and ask once you add this behavior, it's just a whole other huge project. Right now, what I was presenting was just about the structure, but once you incorporate the behavior and you talk about the relation between those two, it's a deep topic.
Christian, have you thought of Cartesian multi-categories instead of this growth and deconstruction of the sorts and the algebraic theories?
Oh,
because they basically make sure that your maps send sorts to sorts.
Oh, okay.
They give you Cartesian multi-categories, and then there's a certain there you can talk about closure there also. You can say maybe certain objects are exponentiable in the same sort of way.
That sounds like what we want. Yeah.
Yeah, it's I think it's a little easier, but I don't know if it's a good, yeah, it's worth looking into. Also, I guess I didn't understand a major thing, which was how should I think of these sieves in terms of like the legal names, something with namespaces, or
yeah. Well, I'm not sure what slide would be helpful, but a sieve is a subfunctor. So if we have n here, then we are getting a subfunctor of the representable on names, which for each other sort that you plug in, you're going to get a subset. So if we plug in one, just the terminal object, then we're getting a subset of names. So that's the simplest level where there are no free variables, and we're just talking about some subset of names which we care about. It's just that sieves are dealing more generally on this level of subfunctors, so you can take in any context you want. But they're like a horizontal categorification of subsets.
Mm-hmm. But the S that is sitting there could be an arbitrary product of exponentials or whatever.
Yes.
And if I had a product of exponentials sitting as S, and I looked at the sieve, or the set of sieves, maybe I have one sieve or something. How do you think of that as like certain kinds of programs, or like some rule on programs or something?
Yeah. Yeah.
Uh-huh.
Yeah. So
and that's what you.
I mean, in general, yeah, you're getting something like relations on these big tuples of contexts that could all have as many free variables as you want. So in general, when we were dealing with all the lax structure, we were kind of going the other way and dealing with the boring relations that are rectangles, you know, just taking subsets and then pairing them. But in general, you could deal inside of the products and exponents and explore very interesting relations in there.
And the fact that these are Presheaves instead of co-Presheaves, I mean, the contravariance is that about like programs that have already gotten you this far? Like you're pre-composing with programs somehow in the sieve. What's that about?
Yeah, so if you're talking about being closed under pre-composition, then the way that you're constructing the sieves is from the outermost constructors. So for example, for a singleton sieve, if you took the multiplication for a monoid, it would generate the sieve that just said, give me everything that is the product of two things. But those two things could be whatever you want. So you're dealing with the outer structure. In theory, yeah, you could also do this going the other way and deal with the co-Presheaves and start with the inner structure. And it would be really interesting to see the relation between those two.
Great, thanks.
Yeah. Other questions? Thoughts?
Okay, anybody else? Somebody saying they'll catch up and come to the Zulip discussion.
Okay.
Are there any more live questions or comments? Yeah, there's a question. Remy is asking, is there a reflection associated with the construction of omega t?
A reflection. Sorry, in what sense?
Remy, could you please clarify?
A reflection.
As in reflective subcategory. So suppose left to join to the inclusion functor.
I'm not sure which inclusion you're talking about. Were you talking about this theorem here where we were including this stuff? If you were talking about this, this was just a way of packaging up some data. So there's probably not anything too nice going on here.
No, so I'm talking about, so I see constructions of models as, you very often you construct a reflective subcategory to construct models, and here you constructed a model of a theory, and I'm just trying to see how I can, I don't know, I'm trying to see a sort of universal construction behind this omega t.
That's a good question. Yeah, whether this has some universality in the category of models of T and posets.
Yeah, I feel like you're forcing operations.
Yeah.
Right. So yeah, usually there's a reflective subcategory. Maybe it's weaker, but
yeah,
I was wondering if there's such construction.
Yeah, that's interesting. I'm not sure. One thing that I forgot to mention is that another very natural question is, what about the models? I didn't mention the models this whole time. How do you? Right now, we were using theories that were rich enough that that it was interesting to just think about sieves in there. But in practice, you would want to be able to transfer these subobjects to models of the theory, and I do have a sketch of how that's going to work, but I think it will end up being kind of an interesting deep story, because you can think of theories as certain operads, and then Presheaves are right modules of an operad, and models are left modules of an operad, and there might be some really cool story up at that level.
Mm-hmm. Thanks.
Mm-hmm. Thanks for the questions.
Okay, anything else? Okay, if there are no more live questions, then let's move the discussion offline. Feel free to ask whatever you want in the Zulip thread. And for now, let's stop the live streaming and the recording. Whoever wants to stay online, we're going to have breakout rooms for a while.
All right.
For now, well, let's thank our speaker again. Thanks a lot, Christian.
Thank you.